Alright, this is lecture 39 and we were discussing droplet combustion. We discussed droplet vaporization and we found the droplet evaporation rate. We also understood what is an evaporation constant and how to calculate the droplet lifetime. So we are trying to do something similar for droplet combustion, and we made some progress yesterday, and we wrote that continuity equation which gives you m dot equal to constant. I said that it's very similar to what we did for droplet evaporation. Other than that, I told you towards the end of the class that we also have to write fuel mass fraction conservation equation and also oxidizer conservation equations, and then we also have to write the energy equation to get temperature. So the picture that we have to keep in mind is something like this, like yesterday. Yeah, so we have the droplet, and between the droplet and the flame, this is the flame, between the droplet and the flame there will be a temperature increase, and then after that it reaches the flame temperature and then it keeps coming down. What I said yesterday is that, okay, we are interested in the m dot, which is equal to m dot f. M dot everywhere in the domain is the same, and that is equal to m dot f, which is the mass flux of the fuel. And I said that getting this is not going to be straightforward because the m dot is determined by the temperature gradient that you get at the surface. So we have to determine this temperature profile, and if you want to get this temperature profile, we have to write conservation equation for this. Plus, we also said that the droplet, will assume the droplet not to be at the boiling point temperature, make it more general, and say that the droplet surface temperature is some Ts, and corresponding to that Ts, there is a YF at the surface. So the fuel mass fraction at the surface. Surface meaning this particular blue one which you see, that's the interface between the droplet and the gas phase. So there you have temperature Ts and fuel mass fraction YFS. So to get that m dot, we have to get this profile, and to get everything in place, you need to actually calculate TF, RF, TS and YFS. So we'll have 5 unknowns which we'll have to solve. We still haven't seen how exactly to set up all these equations. One equation that we understand will be important is the one which we saw yesterday. Now this is the droplet surface, and at the surface we know that there is some enthalpy carried by the fuel coming to the interface, and then there is some enthalpy which is going out because of the vaporization of the fuel, and then there is also transfer of heat from the gas phase to the interface, and also transfer of heat from the interface to the interior of the liquid. So if you think of a droplet, we can expect that the center of the droplet will be at a lower temperature than the surface of the droplet, because the surface of the droplet is closer to higher temperatures. So in general there will be a Q dot I to L, interface to liquid, but we will most likely we don't need to use it so much because we are looking at the simplified description of the problem. So we are trying to keep things as simple as possible. So we'll set Q dot I to L to 0, and if we do that, then the droplet surface energy balance is Q dot G to I equal to m dot into HFG. So this is very similar to what we had got for droplet evaporation case. But of course there is complication. It is going to be more difficult because to get Q dot G to I, we need to know this conduction heat flux which will go into the droplet surface by virtue of the temperature gradient that we are getting. Okay, so this discussion we had in the last class. Now we also need to work on other equations, because we have the energy equation and we have the surface energy balance, but there will be other equations required because we have to get all these 5 things, m dot, then YFS, TS, TF, RF, everything. To get all this, we have to increase the number of equations that are available to us. So one thing that we can do is to try and set up a fuel vapor distribution profile. That is, we can try to get YF as a function of R. Now, where will YF vary? YF will vary in the inner region. What is the inner region? From the droplet surface to the flame. There you will have variation of YF. Beyond that region, that is beyond the flame, you will not have fuel mass fraction variation, because we are assuming that the fuel mass fraction goes to 0 at the flame. So we are assuming that the reaction is very intense at the flame, which gives you an infinitesimally thin flame sheet. So this is called a flame sheet approximation. In combustion literature, if you come across flame sheet approximation, that essentially means high reaction rate and a thin flame. So we are assuming that. So we are interested in only YF in the inner region. So how do we get YF in the inner region? So in that inner region, we can say that m dot fuel double prime is m dot double prime into YF minus rho d dyf dr. Okay, so is this familiar? What is it? What is m dot f double prime? Mass flux of the fuel vapor. It's actually positive from the droplet surface to the flame, radially outward. What about m dot double prime? Total mass flux. So this m dot double prime is actually m dot f double prime plus m dot product double prime. Okay, because in the inner region we have fuel, vapor as well as products. So that is m dot double prime. Actually, these mass fluxes are in fact vectors, in the sense that the fuel mass fraction is fuel mass flux is going this way, and in general the product mass flux is coming in this direction. So actually, when we are writing m dot f double prime plus m dot pr double prime, we have to be careful about the signs that we are taking. But here it so happens that we can say m dot pr double prime equal to 0. So why is it so? So that m dot double prime becomes equal to m dot f double prime. So is this okay to write? Yeah, it's okay to write because of the reason that we discussed yesterday. Yeah, so the product forms a stagnant layer between the droplet surface and the flame. And why is it so? Because the product cannot go and move into the droplet and get dissolved there. So it's a good assumption to say that the product gases will not get dissolved in the liquid fuel that you have. So there is no m dot pr double prime. So that is equal to 0. So if that is 0, then this equation that we have can give you a differential equation for YF. Okay. Now before we do that, you have to let me know whether this is okay. I mean, do you remember this? Okay. So what is it? This is the mass flux of some ith species, in this case fuel, and that is equal. That has two components. Remember, this has a bulk flow component. So the mixture is taking it along, but with respect to the center of mass of the mixture, there is also diffusion. So the diffusion term is taken care of by this term, which is given by Fick's law. So minus rho d dyf dr. So this is m dot by virtue of diffusion of the fuel. Correct? So the advection, the bulk flow component and the diffusion component together give you the total m dot f double prime. Correct. So we can then from this we can actually easily get this expression, we can get m dot f equal to, I am jumping one step, but that should not be a problem. Is this possible, you think, from what we have? Yeah, so this m dot double prime is actually m dot f double prime, and if you take this term on this side, you will get 1 minus yf. So that explains this 1 minus yf, and this 4 pi r squared is because we are converting from flux to flow rate. Okay, so this is the equation that we are getting from for m dot f for m dot f. So this is the equation, and we want to get yf distribution as a function of r. Okay, because we are trying to increase the number of equations that we have. It will be of some use to us. How do we get this? We can integrate this. This is a first order differential equation. In fact, m dot f is taken to be constant. So this can be integrated easily, and we can get yf as a function of r, valid only in the inner region. So that will require, integrating that equation will require boundary conditions. So we can use these two. These are the two boundaries, isn't it? These are the two boundaries, RS and RF, inner region. Okay, so this is YFS at corresponding to TS. Not multiplied, this doesn't mean multiplied, this means YFS corresponding to the temperature, surface temperature TS. And what is YF at RF? 0. This is 0 because we are taking the flame sheet approximation. There is no fuel which will exist at the flame. At the flame, it's all products. Okay, fuel and oxidizer come, they react vigorously, and they give you all products. So what happens at the liquid vapor interface at the droplet surface? At the liquid vapor interface, we will assume that there is liquid vapor phase equilibrium. So there will be some equilibrium established out there, and that equilibrium will determine what is the temperature of the surface Ts and what is YFS, that is the mass fraction of the fuel species at the surface. So we are not assuming that this is a situation when the droplet is reaching the boiling point. So we are making it more general. So the droplet temperature is some Ts. Within the droplet, there is no variation of temperature. So we made that assumption. As I said, the droplet center can be at a lower temperature, droplet surface can be at a higher temperature, but we are neglecting that part. So we are saying that at any instant of time, droplet is at a uniform temperature, and that temperature is equal to Ts, which is the surface temperature, and that temperature is not by design equal to the boiling point temperature. We are making it more general. So this is some temperature which is determined by, amongst other things, the liquid vapor phase equilibrium at the interface between the liquid droplet and the gas. Okay, so we will bring in phase equilibrium. Fine. That phase equilibrium, how to incorporate that will also come in the discussion sometime later. So we are writing boundary conditions, and we had on the previous page we had the differential equation for YF. So there was this dyf dr. So it can be easily integrated, and this integration will give us YF as a function of r. So this ZF is just a shorthand, and after integration you will get this. This is inner region solution for fuel mass fraction. Again, don't need to write this because this is available exactly with the same notation in Turns's book. Now we'll do the outer region also. For the outer region, we understand that we'll have to solve for the oxidizer species equation. Outer region, oxidizer species mass fraction as a function of the radius. Okay. So what will the boundary conditions be? At RF, Y oxidizer is 0, and where is the other boundary? Infinity. At infinity, YOX is equal to 1, because there is nothing else, because the fuel in any case it's consumed at the flame. Fuel cannot go out there, so it will be equal to 1. So to get this, again we'll do the same thing. We'll write m dot oxidizer double prime is equal to Y oxidizer same logic. Actually, if you look up Turns's book, you will see that this m dot OX double prime is written in bold. Okay, printed in bold letters. That means these are vector quantities. All right. So strictly speaking, you should put something like this, like vector, and this m dot OX double prime is this is the chemical system that we have. So this m dot x double prime will be minus nu m dot f double prime, and m dot product double prime will be nu plus 1 m dot f double prime. Okay. So what have I done? First, this is fine. This is the same logic. This is the oxidizer flux, has two contributions, one due to the bulk flow and the other due to diffusion, mass diffusion. And these two terms, that is within brackets, you have the total mass flow, correct? But think about the mass flow beyond the flame, right? Beyond the flame, which way is the product moving? Radially outward. And which way is the oxidizer moving? Radially inward. So that's why you will see that oxidizer has a negative sign, because plus means radially outward. For example, in fuel also we took plus, like m dot f double prime, we took it to be in terms of a plus quantity, which is radially outward. So since it is oxidizer, it's moving radially inward, so it has a negative sign. And product has a positive sign. How do you know that it's nu times and nu plus 1 times? From this expression. Okay, so the oxidizer has to come and move in a certain proportion, right? Certain proportion and proportion to m dot, and that's actually the stoichiometric proportion. Diffusion flame, so that's what we know from here, that we have to use the stoichiometry to relate m dot OX double prime with m dot F double prime. So we get this, and then that means we can write everything in terms of m dot F, because we can replace this one in terms of m dot F, we can replace this one in terms of m dot F. So we can bring everything in terms of m dot F, correct? And then finally, again with little bit of work, which I will have to ask you to do, we get this, we know the boundary conditions I just now told you. YOX at RF equal to 0 and YOX R tending to infinity is 1. So, if we do that, we can get YOX as a function of R, correct? Because this is our differential equation, first order, and it is very easy to integrate this. Once we integrate this, we will get YOX as a function of R. YOX So, again please verify. I am leaving out steps because I think I do not need to do all the steps, but please verify all this. Okay. And we did the energy equation, isn't it? What is the energy equation? So, we got today we have got YF as a function of R in the inner region, we got YOX as a function of R in the outer region, and we did the energy equation also previously. So, that is that came from somewhere. What was that? It came from the energy equation in spherical coordinates using a Schwab-Zeldovich formulation. Okay. So, this is the equation that we had, but we will integrate this equation piecewise, like in the inner region and in the outer region. And I think I wrote this yesterday probably. So, this is we get something like this, and so this is another equation. This is temperature as a function of R, and we can get temperature as a function of R in various regions based on the boundary conditions that we have. Boundary conditions, I think you will be able to easily figure out what the boundary conditions are. If you look at the diagram, look at the general picture, this is Ts, this is Tf, this is T infinity. So, you use these boundary conditions to integrate this equation and you get temperature profile. So, that is the idea. And what else do we have? We have done the energy balance at the droplet surface. We have got the fuel mass fraction profile in the inner region. We have got the oxidizer mass fraction in the outer region. And we can do one more thing. We can do an energy balance at the flame sheet. Energy balance at the flame sheet. So, let us see. So, we will think in terms of this particular picture. So, this is a flame sheet, okay, and let's think about what energy, what enthalpies move in there and what happens out there. So, there is an m dot oxidizer, H oxidizer. So, the oxidizer is coming with some enthalpy. There is of course some m dot f into hf. Fuel vapor is there in the inner region. Which side is inner? This is the inner side, right? The droplet is on this side. This is the flame, and this is radially outward. This direction is radially outward. So we have these plus what else? There can be some energy transfer here, which we'll call q dot f to infinity, and then there can be some energy transfer here, which we'll call q dot f to I. Okay, so do we have everything? First of all, let's see, this is the easy one. Oxidizer is moving towards the flame. It has to, because there is zero concentration at the flame, oxidizer is getting consumed. Far from the droplet, there is enough oxidizer concentration, so the oxidizer has this concentration gradient, because of which it can easily move towards the flame. So this oxidizer, when it moves towards the flame, it brings in some enthalpy with it, which we are calling H oxidizer per unit mass. So m dot OX multiplied by H OX is what the oxidizer is bringing to the flame. Similarly, m dot F into HF is what the fuel is bringing to the flame. Okay. Now, what about this? What is Q dot F to infinity, you think? Let's think about the flame. What is happening out there? Fuel and oxidizer are meeting, they are reacting. And at that location, the chemical energy of the fuel is getting released in the form of thermal energy. Where is that energy going? So it will go both sides. No, if this is the flame, so it will move this way, radially outward, but it will also move this way towards the droplet. Fine. So what is Q dot F to infinity? It's the energy which is going from the flame towards the outer part of the surroundings, outer region. It going towards infinity. And how can we calculate this? How can we write this in terms of things which we know? We can use a temperature gradient. Okay. We have used temperature gradient to calculate Q dot when we did that energy balance at the droplet surface, isn't it? The energy which goes into the droplet was written in terms of K into area into dTdr at the droplet surface. We have done that. So we can do something similar here. Do we have a temperature gradient? Yeah, so we have a temperature gradient. We have this temperature gradient. So if we can get the gradient at the flame, then we will know that there is some Q dot F to infinity going out. And similarly, should we have a Q dot F to I, flame to inner region? Okay. So that is again from the temperature gradient, which will use this part of the temperature profile. Okay. Yeah.
Like this Q dot F, both sides we can definitely calculate from the temperature distribution. But we have not yet used the chemistry. Like we would have also said that this heat release is due to the QCV, the heat release due to combustion of fuel, something like that. Could not we have been that concept?
Yeah. So his question is, the question that has been asked is, where does the heat of combustion come here? Actually, we don't need to bring in the heat of combustion, because heat of combustion, if you bring in the heat of combustion, then to account for the total amount of energy released, we have to write m dot into delta Hc. Okay, that sort of thing. But that doesn't tell you which on how much is going away from the droplet into the outer side, and how much is moving from the flame towards the droplet side. So we want that sort of an information here. So that to get that information, we are trying to use the temperature distribution. Now, coming to your question again, will these terms somehow relate to what you just now asked? And am I missing something? Okay, so I have actually intentionally left out something. What is that? Products. Okay. So, products are going out, right. So, we have to write something like m dot product to each product. Okay. And we can do this complete balance, all right. So, how do we write these things? We add those arrows, terms with arrows which are moving towards the flame, and equate that to the sum of those quantities with arrows which are moving away from the flame, right. So, we can do that, and we will get a delta Hc actually, we will get a delta Hc, because that was his question. How will that come? There is m dot f here, there is m dot oxidizer here, m dot product here, but m dot oxidizer, m dot product can also be written in terms of m dot f, and ultimately you will be able to write something like differences in enthalpies come moving in and moving out. So, we will be able to bring in delta Hc. Okay. But that is not the only point, because we are trying to see how much is, how much of that is going in the inward direction, how much of that is going in the outward direction. So, we will have to bring in, for these two terms we have to bring in temperature gradient. Okay. So, the temperature gradient that we will have is, this will use dt dr at Rf plus, that is on this side. Rf plus means slightly beyond the flame, okay, just on this side of the flame, and this will use dt dr Rf minus. Actually, these two things come from two different pieces of temperature profile, isn't it? So, these two different pieces of temperature profile are this and this, correct. So, if we do all of that, then we will get the balance that we will get will give us one equation. So, that will be an equation for flame sheet energy balance. We are trying to build the number of equations. So, we have the droplet surface energy balance, we have the fuel mass fraction profile in the inner region, we have the oxidizer mass fraction profile in the outer region. Now, we are getting a fourth equation, which is the flame's energy balance. So, the flame energy balance is essentially this, which will use dt dr at Rf plus and dt dr at Rf minus, and we know T as a function of R, in some form, because we integrated the energy equation, right. I did not write the full form of that, but I told you that okay, there is an energy equation which is an ODE, integrate between flame and droplet and flame to get one piece of the temperature profile, then integrate between the flame and the surroundings to get the other temperature profile. So, we have both the pieces of temperature profile. So, we can do this and we can do this also, this gradient also, right. So, after doing all that, we will get one equation for flame sheet energy balance. Okay, again, this is a long one, you do not need to actually write this down because it is available. Something like this. Please check against the book if I made some mistake. I was just trying to quickly write this. Don't have to remember any of this, but it's just important to know that this contributes an equation. What are our unknowns again? Let's recall. What are the unknowns? The 5, right? What are we trying to find?
ES.
First, tell me the most important one. M dot, isn't it? And TF, RF, then TS, YFS. Okay, we were doing all this.
This will find this function of RSS at any point.
So this is a quasi-steady model. So this is like saying that the droplet has a radius of RS. Okay, and while it is at RS, it is establishing in the gas phase these temperature profile and fuel mass fraction profile and oxidizer mass fraction profile. All right. So the time factor has not been brought in. Time factor will come again like the droplet evaporation problem. It will come towards the end. When we try to find the droplet lifetime, how did we do that? We said ddt of the mass of the droplet equal to minus m dot. We did that for droplet evaporation. So we will do something like that. That will bring in this time. As of now, it's as if you have a droplet of radius RS. And corresponding to that, we are getting all this profile. RS, of course, changes, but that is not explicit in all this. That will come later. So we have 4 equations actually. To get these 5 things, we have got 4 equations, and the 5th one will come from the energy. It will come from the phase equilibrium at the interface. Which interface we are talking about? This droplet. So this is the interface we are talking about, and we'll assume that liquid vapor phase equilibrium exists. So you'll get some YFS here, which will be dictated by phase equilibrium. So this is not chemical equilibrium, right? You studied phase equilibrium in thermodynamics, so we are talking about that phase equilibrium. And we can use a familiar equation for this. You can read about this equation from a thermodynamics book. This is called Clausius and Clapeyron. Clapeyron. So this is Clausius-Clapeyron equation, which we will describe the liquid vapor phase equilibrium at the interface. So what that tells us is PFS is, in very simple terms. So these A and B are some constants which depend on some properties. Okay, but this is roughly what it is. Now, what is PFS? It is the partial pressure of fuel at the surface. So PFS is actually chi Fs into pressure. Pressure is the same everywhere. So this is this droplet, okay, in the surroundings where combustion is taking place, pressure is not changing. All right. So it's, what is it doing? The Clausius-Clapeyron equation. It actually, it's connecting to some fuel concentration here with the surface temperature, right? Because this is chi Fs into pressure, and pressure is known. If it is happening at 1 atmosphere, it's 1 atmosphere. If it's happening in engine conditions, maybe it's 10 atmosphere, 20 atmosphere, whatever, then it's that pressure. So that is known to us. Pressure is uniform. So this connects the mole fraction of fuel at the surface to the surface temperature. Okay, so this is the phase equilibrium argument. Now, we are actually done, except that we are not really comfortable with mole fraction in this analysis, because we have been using, in this analysis, we have been using mass fraction. Okay, that's all. So we have to convert from mole fraction to mass fraction. And yeah.
In case
Hmm.
Is it medium between liquid and vapor?
Hmm.
Then shouldn't it be boiling temperature?
No, no. It will be actually, it can be shown that if the ambient temperature is really high, then the Ts approaches the boiling point temperature. Otherwise, it's governed by this relation. Okay. This will require some analysis to answer your question, but it can be shown that if the temperature is really high, okay, think about the droplet evaporation problem. If T infinity is really high, then the assumption that the surface temperature is equal to boiling point temperature is good. Okay, not otherwise. So we are making it better in the sense that this is a more realistic assumption. So in general, we cannot say that it will reach the boiling point temperature. There will be some difference. And what do we want to do now? We want to bring in YFS here. And how to do that? Yi, we are going to bring in, instead of mole fraction, mass fraction. So Yi is chi I to this. How do we convert from mole fraction to mass fraction? Mole fraction to mass fraction. You take the mole fraction multiplied by Wi divided by W mix, you will get the mass fraction. Correct? So you can do that, and if we do all of that, then we will be able to get an expression where YFS and TS are related by one expression. Correct? Using Clausius-Clapeyron. So again, little bit of work. After a little bit of work, you can show that YFS again you can verify. So for the mixture molecular weight, we have done something. We have taken fuel products and all that. So ultimately, this is what you get. Now, what is the summary of the situation? Summary of the situation is that we have unknowns m dot, Tf, Rf, Ts, YFS. Correct? This is the full picture that we have. And to get these, we are trying to use 5 equations. And those 5 equations are, to repeat, energy balance at the droplet surface, fuel species equation in the inner region, oxidizer species equation in the outer region. We have flame sheet energy balance and liquid vapor phase equilibrium as described by Clausius-Clapeyron equation. So that gives you 5. So if you use all these 5, then you will be able to solve for m dot. Okay. So this is the picture. Now the book has a table. I forget which one. What's the table number? I don't remember right now. So that summarizes this situation, which I just now told you. 5. What are the 5 equations and what are the 5 unknowns? Please take a look at that. We'll do that tomorrow in any case. But maybe before we close, we want to just look at one short video. There's a bit of a problem. It's not coming up. स्क्रीन नहीं हो रहा. कौन तो है
स्टैंड बाय चला टाइम लेता है सर.
ठीक है. Yeah, so it took me a little bit of time now. We are actually running short of time. I guess you have another class now, but very quickly. This is a video made by Indian Institute of Science, IISc. You can just read the text here. So these two black triangular sort of things, these are actually the electrodes. So they give the spark, and they did experiments with different kinds of fuels. We'll follow this red dot which is running down that line on the left hand side. Okay. What is it showing? It's showing a d squared law. So some practical fuels also like diesel, gasoline. So ethanol flame is like you can almost see through it, where the others actually you can't really see through them. There's a lot of radiation coming from this. Okay. So as I said, this is available in YouTube, and these experiments were done in normal gravity. So you can see the flame, which is more like this. Okay. So this is the source, and then more like this, right? But if you do experiment in an atmosphere where there's less gravity, then it becomes easier to study because there is no disturbing flow. Remember, in the analysis that we have done, we have assumed that there's no buoyant flow, there's no effect of gravity. Okay? So our flame is actually not like this. Our flame is, you have the droplet and you have a flame around this, which is easier to study because this is then just a spherical coordinate where variations are in radial direction. So all equations had only DDR, wasn't it? There was nothing else. Because if you get this shape like this, there is buoyant flow, it becomes more complicated. And to understand liquid fuel combustion better, people have done experiments with where there is less gravity, and if you can do that by making an instrumented box and have liquid droplet suspended there somehow, and then the droplet can burn, you can drop the box from the top of a tower. Okay, this is sounds simplistic, but that is what is done actually at space agencies. For example, at NASA or at Japanese Space Agency, this is what they do. And if you do that, then you get the spherical flame which we are talking about. And so these are called free fall experiments, and you get very short duration of time when it's falling, the box is falling with the droplet, with a burning droplet in it. So the amount of time that you get in low gravity is the time that it roughly takes from falling from that height to the ground level. So that is maybe 1 or 2 seconds. So I'm going to show you quickly results of some experiments done by Cornell University researchers. So the droplet is moving a little bit. Now it gets a spherical flame. Okay. All right. So let's see this. The droplet, and then it gets its spherical flame, and towards the end you see that it's producing some amount of soot. The particles which you see, these are soot particles. This is for heptane. And this is a free falling case. So this was done by Professor Tom Abedisian at Cornell University, probably funded by NASA. I don't remember right now. And then there is another one which is toluene. So what does this tell you? That this is also spherical combustion, but it produces a lot of soot. Compared to heptane, toluene in this example, toluene is producing much more soot. All right, so we are running out of time. We'll stop here. Thank you.